Okay, good day. This is AP Calculus. I'm Mr. McCully, and this is the second part of section 3.7 optimization problems. So let's get right to it. Okay, so this one is a little bit more challenging, and it's going to take us a little bit of time, but we're going to try and crank it out here real quick. So this is a question from from the textbook, and I'm not sure what the number is, but we will move on. And it says, find the area of the largest isosceles triangle that can be inscribed in a circle of radius 6. So this is an isosceles triangle, and these two base angles are equal. That makes it isosceles. And they want me to solve this function by writing area as a function of h. So let's talk about the area equation just to begin with, and we all know. We know that A is equal to 1/2 base times height, but h is already this part, so I'm just going to say AB, and we'll say that A is this length right here, and so it is this altitude value, and so I can rewrite that as 1/2 of 6 plus h, and that will be our height, our altitude, and then our B value will be right here. And we have to figure that out. Now, the good news is that since it's an isosceles triangle, these two triangles right here are congruent. We have side, angle, and then angle congruency, and that's allowed. And so we can say that this side and this side, those two base sides have to be equal. And if we can figure out what one of them is, we'll just multiply by 2. So if I call this C, we can use Pythagorean theorem and say that h squared plus c squared is equal to 6 squared, because we have this right triangle. The 6 is the hypotenuse, and the h and the c are the two sides. So I'm trying to solve for c right now, and so I've got c squared will be equal to 36 minus h squared, and then c would be equal to the square root of 36 minus h squared. Now again, since c is only half of this entire value for b, I'm just going to multiply this by 2 and say that it is 2 square root of 36 minus h squared. And so the good news here is that my halves, they cancel out. That's great. Or the half and the 2 cancel out. That's a better way to put it. And then I'm going to rewrite this radical as a rational exponent. And I'm going to say that 6 plus h times 36 minus h squared to the 1/2 power. That's my area equation in terms of just this h only. All right, so let's go back to what we're doing. We always need to, kind of circle back. We're trying to find the area of the largest isosceles triangle. Now let's talk about h. Okay, if h is 0, you have a base, or your base will be the entire diameter, and then you'll have two sides there. If h ends up going all the way down, if h becomes 6, well, these sides will actually come down and collapse because our base side will shrink down to 0. The further down we got, and I'm just going to kind of see that, and then I'd have those sides there. So the longer h is, the shorter the base would be. How much of that will delete? Okay, we're good. So where do maximums and minimums occur? Well, it occurs where there are critical numbers. So let's take the derivative of this thing, and we have a product of two functions, and one of those functions is a composition of two functions. So we're going to have to do both the product rule and the chain rule. The derivative of 6 plus h with respect to h is just 1. And then we would leave the second function alone, so 36 minus h squared to the 1/2 power, plus, now we would leave the first function alone, which would be 6 plus h, and then we would multiply that by the derivative of this second function. Now, because it is a composition, we're going to have to do the chain rule. I bring down the half, and then it is the inside left alone, so 36 minus h squared now to the negative 1/2. And then I have to multiply that by the derivative of what's inside. Now the derivative of 36 minus h squared is just going to be negative 2h. And again, we have a half and a 2 that cancel. And so rewriting this, probably going to need 2 steps, but 1 times anything is just that anything. So I'll leave that 36 minus h squared to the 1/2. And then because of the negative exponent, this 36 minus h squared to the 1/2 goes to the bottom. So 36 minus h squared to the 1/2 on the bottom. And then I have this negative h here. So I'm going to put a negative out front, and then I'm going to distribute. We're going to go h times 6 is 6h, and then h times h is h squared. All right. Now I've got a fraction and a number, and I need to add them. So I'm going to have to come up with a common denominator. Now luckily the common denominator, because it's 1, is just going to be 36 minus h squared to the 1/2. So I'm going to multiply by a funky 1. It's going to be 36 minus h squared to the 1/2 over 36 minus h squared to the 1/2. Now what's good about that is we have our 36 minus h squared to the 1/2 on the bottom for both fractions. But if you remember your properties of exponents, if I go a to the 1/2 times a to the 1/2, I add my exponents, which would give me a just to the first. Well, if I multiply, that's not a very good 2. If I multiply 36 minus h squared to the 1/2 times 36 minus h squared to the 1/2, I get that to the first, and so I can get rid of those parentheses and say it's 36 minus h squared now to the first, and then it'll be minus 6h and then minus h squared. So this thing is 36 minus 6h and then minus 2h squared all over 36 minus h squared to the 1/2. All right. So just because I've already worked this problem out, you could find zeros of this thing using the Pythagorean theorem, but it is factorable. If I factor out a -2 and then put it in the standard form, I'll get h squared plus 3h and then minus 18 all over 36 minus h squared to the 1/2. And then that thing would be, let's see here, it's -2 and then 2 factors of 18. One's got to be positive, one's going to be negative. That add up to 3. 6 and 3 work. So let's go. It'll be x. That's not x, it's h. We've been doing good so far. Already screwed up. So I've got h, and it'll be plus 6, and then h minus 3. It's my factorization. And then 36 minus h squared to the 1/2. Now my critical numbers here. What makes the numerator 0? Well, -6 makes the numerator 0, and +3 makes the numerator 0. What makes the denominator 0 or undefined? I get plus or minus 6, so I'd add my plus or minus 6 there. Now, we could normally test these values, but if we think contextually, what's happening here? H is a length. If h is positive 6 units long, it's going to be another radius of the circle. So these two sides are going to be touching and they become diameters. So there would be zero area for that one. If h becomes -6, well, it's going backwards along this segment until it goes back 6, and it'll be touching this side of the circle or this edge of the circle at the vertex, and it'll also have a 0 area because there will be no length on any of those two isosceles sides. So we know that the value that it's going to make it true is going to be x, not x, I did it again, sorry, will be h equaling to 3 maximizes area. And that's good. We know that it has to. And if we wanted to, I think the question asks us to find the maximum area. Well, here's our area equation. So I could go A equals, let's see here, it'll be 6 plus 3, and then 36 minus 3 squared to the 1/2, which would be 9 times 27 to the 1/2, which would be 9 times 3 times 3 to the 1/2, which would be 27 square root of 3. That's my maximum area of an isosceles triangle. All right. Now, what's kind of cool about this, though, is that if you were to calculate these sides, and I'm not going to do it just for time's sake, I'm already 10 minutes in, but if you were to calculate these sides using an h of 3, and you would calculate that side, and then you could use Pythagorean's theorem to calculate, it would be 9, and then whatever you got here, c is square root, or 3 square root of 3, and then it would be times 2, and so you would get 6 square root of 3, and all three of these sides ends up being 6 square root of 3. So the length here that makes it optimizes our triangle's area is a length that causes this to be a equilateral triangle, which is kind of cool. All right, that's the first one. Doing well so far. So I'm just gonna, you know what? I'm not gonna erase the whole thing. I want this area equation as a starting point. That way I don't lose. And we're just gonna erase, and we'll do B. I'm gonna do some trig stuff. And B is kind of tough, and there's a little bit of visualization that you have to do, but we are still going to start with this equation here as our area equation. And so I want to, first thing I want to do is, let's erase this. I want to talk about just this little triangle right here. So I'm going to draw it in here. This triangle. It's just a miniature version of it so we can see it. And we can talk about it without all this other stuff. This distance here is alpha. And then this distance here is 6 plus h. And this distance we said was 36 minus h squared square root. All right. So if I want to use this angle to represent all of these sides, I kind of need to know this third side in terms of what I have for h. So I'm going to call it, I can't call it a or b because I've already used that. So let's call this side d just for right now. And so 6 plus h squared plus the square root of 36 minus h squared is equal to d squared. Now when I multiply all of this stuff out, I end up getting, let's see here, let me make sure, because I'm going to have, oh, we'll just do it. I'll go. So this would be 36 plus 12h plus h squared, and then this one would be plus 36 minus h squared, and then that's equal to d squared. And so my h's cancel here, and I'll have 36 plus 12, oops, I screwed that up. 36 plus 12h is equal to d squared. So d equals the square root of 36 plus h, or 12h. Yeah, that's what I want. D equals the square root of 36 plus 12h, and then I can factor out a 12 from both terms. And when I factor out a 12 from, no, I screwed up. Sorry. I'm sure you guys see it. 36 and 36 is 72 plus 12h equal to d squared. And so d will equal the square root of 72 plus 12h. Now I can factor out a 12, and 12 has a perfect square that's a factor that's 4. So this can actually reduce, and I'm going to do this just so that we can see, and normally I wouldn't reduce this, but I need to show you something. So I factor out a 12 and simplify, and so I get 12 square root of 3 times the square root of 6 plus h. And that's my value here for this side D. Ends up being, let's see, right here, it's going to be equal to square root of 3 times the square root of 6 plus h. All right, and I need that because I have a 6 plus h here. All right, so let's talk about two trig functions, and we're going to use that to represent our angles. I know that the cosine of alpha, cosine is is adjacent over hypotenuse. In this particular instance, it ends up being, let's see here, my adjacent side is 6 plus h, and then my hypotenuse is that 2 square root of 3 times the square root of 6 plus h. Now, here's some of the funkadoo stuff. I can actually divide this by 6 plus h to the 1/2. And when I divide 6 plus h to the 1 by 6 plus h to the 1/2, I get 6 plus h to the 1/2 on top, and the 6 plus h on the bottom cancels out. So I got square root, or 2 square root of 3 on the bottom. Excuse me. Sorry about that. And then I can bring that 2 square root of 3 over, and I can say that 6 plus h to the 1/2 is equal to 2 square root of 3 times the cosine of alpha. And that's just me taking 2 square root of 3 and multiplying both sides by that. All right. And then I put this out front. Now, the tangent of alpha is equal to opposite over adjacent. And so the opposite side from the last one we said was this, it was the square root of 36 minus h squared, and then it would be over 6 plus h. All right, and so I can solve for 36 plus h, or 36 minus h squared to the 1/2 by multiplying that over, and then I will get the square root of 36 minus h squared is equal to the tangent of alpha times 6 plus h. And just to keep my variables the same, we use a lot of thetas, but this problem had alpha in it, so I didn't want to change my alpha. And hopefully you didn't go, where do you get theta from? It's that alpha. Okay, so here's why I did this. It's so I can use these two things right here as substitutions into this function. All right, I am going to substitute in for 6 plus h, our cosine value. So if I do that, I've got my a. Oops, let's go back to the regular pen. If I do that, I got a equals, and so I've got my 6 plus h. I'm just rewriting this one. It'll be 36 minus h squared to the 1/2. All right, so 36 minus h squared to the 1/2 is 6 plus h is tangent alpha times 6 plus h. So let's rewrite. I've got 6 plus h now squared times tangent alpha. Now 6 plus h to the 1/2 is 2 square root of 3 cosine theta. Well, if I have squared, then I have 4 6 plus h to the 1/2. So I can change this 6 plus h squared to 2 square root of 3 cosine alpha to the 4th tangent alpha. And I know that that looks crazy. And if I multiply this out, I can say, if I take 2 plus 3 to the 4th power, or 2 square root of 3 to the 4th power, I actually end up with 144. So I get 144 cosine to the 4th alpha tangent alpha. That is my area equation. And I know that's a mouthful, but it is what they asked for. They said area as a function of alpha. Excuse me. And that's what I have here. And so just like in the other problem, to find a maximum or minimum, we have to take the first derivative, and we have to test our critical numbers. So our A prime, our area prime, with respect to alpha this time. Well, now I have a product, and I have a product with a composition. I've got cosine to the fourth. And remember, cosine to the fourth alpha is the same as cosine alpha to the fourth power. And so there you can see the composition a little bit better. So I'm going to leave this 144 alone, and I suggest that you leave your bigger numbers outside as coefficients, and then we're just going to deal with this. And so the derivative of the first is going to be 4 times the cosine now to the third of alpha times the derivative of what's inside. Now the derivative of cosine alpha is negative sine alpha. And now we multiply that by the tangent of alpha. We're leaving the second one alone. And now we leave the first one alone. So it'll be cosine of to the fourth alpha. And then we do the derivative of tangent, which we know to be secant squared of alpha. Now we want to know where this thing is equal to 0. Okay, so let's see here. There's some simplification that I can do here. Remember that secant squared alpha, or just, you know, I don't even need to do that. Secant alpha is equal to 1 over the cosine of alpha. So here I can actually cancel out a couple of these values here, and I can say that this thing, I can cancel out, I got 4 cosines on the top, 2 cosines on the bottom, so I can say that this is cosine squared alpha. And then let's see here, I've got, tangent is, remember that tangent alpha is sine alpha over cosine alpha, and so I've got a negative sign on the top. Let's see here. I'm going to cancel out. I'm going to cancel out one of the cosines with the cosine on the bottom, and then I got to multiply the sine here with the sine on the top. So that'll give me, and again, I still have my 144 here out on the top. I have 4. It will be cosine squared alpha, and then it will be times negative sine squared alpha plus cosine alpha equaling to 0. Now, we can divide both sides by the 144, and that'll give me 4 cosine squared alpha times negative sine squared alpha, and then I don't know why that's not doing it. So plus cosine squared alpha equaling to 0. And then let's bring that negative over to the other side, or bring this cosine squared to the other side. That'll give me 4 cosine squared alpha. Then just for clarity, I'm going to take this negative and I'm going to put it out front there. And then sine squared alpha equals negative cosine squared alpha. These negatives cancel. And then I've got a cosine squared on the left, cosine squared on the right. If I multiply or divide both sides by cosine squared, they will cancel. I divide by cosine squared alpha and cosine squared alpha. And that will leave me with 4 sine squared alpha. Cosine squared alpha divided by cosine squared alpha is just 1. And I know that that's a mouthful. Okay, I get it. But the good news is, check this out. I get sine squared alpha equaling to 1/4. If I take the square root of both sides, I get the sine of alpha equaling to the square root, or plus or minus, square root of 1 is 1, the square root of 4 is 2. And so I have to ask myself, where is the sine of alpha equal to plus or minus 2? Well, alpha could be, let's see, a half. It could be pi over 6. It could be 7 pi over 6. It could be, oops, I missed one. So 5 pi over 6 is not going to be any of these. And it could be 11 pi over 6. But anything that's bigger than 7 pi over 6 is going to make these obtuse angles. So this thing right here has to be, these are the only one that works. I'll have too many degrees for a triangle because this has to be an angle of a triangle. This is the only one that works. And so again, alpha has to be this pi over 6. And since we have an area equation, this one right here, if we plugged in that alpha and pi over 6 into these two, we'll end up with that same value that we had in the other one, that 27 square root of 3. But here's the crazy thing. Pi over 6 is 30 degrees. So I've got 30 degrees here. This has to be 30 degrees here because I got two two congruent triangles. So that's a 60-degree angle. That leaves 120 left. Since these two have to be equal, 60 and 60, again, we get an equilateral triangle. So that is it. It's crazy. All right, 25 minutes for a second one. That's crazy. Let's see if this Star Wars fun fact of the day makes up for it. What you see pictured here is Frank Oz. He is a longtime actor, acted in a lot of movies, did a lot of bit parts, and he is the voice of Yoda, but he didn't get started as a movie star or as Yoda. What he did get started as was he worked in Jim Henson's Muppet Group, and he is the voice of not only Yoda, but a number of your favorite Muppets. He does Grover, Miss Piggy, Animal, Fozzie Bear, oops, went away from that, Fozzie Bear, Cookie Monster, and Bert from Bert and Ernie. Well, folks, I hope that was worth it. Have a great day. I will see you in class. Goodbye.